Dear colleagues, welcome to our linked live event on advancing brain research through invasive brain imaging methods. I'm Milena Korostenskaja and I will be your moderator for today's session. The question is, how can we study the brain in real time with simultaneous stimulation and seamless brain-computer interface output? For years, scientists have sought a standardized solution to make this possible. And today, we're excited to introduce the CortiQ 2.0 system, a breakthrough in achieving these goals. Please join me in welcoming our guest, Dr. Christoph Kapeller from g.tec Medical Engineering. Dr. Kapeller will be demonstrating the capabilities of CortiQ 2.0. Welcome, Christoph. Thank you so much for joining us today. For some reason, Christoph, I cannot hear you. Let's see what happened.
Hello,
Yes.
Milena.
Yes, now I can hear. Yes,
Thank you very much for having me.
Yeah, thank you very much for joining. And together with Christoph, we will go over several things today. First of all, we will look at the CortiQ 2.0 system setup so that all of you would be able to see how this setup looks like. Next, Christoph will share with us the insights into how CortiQ 2 is transforming brain science through several groundbreaking studies. And then we will see a live demo of CortiQ in action. So make sure to stay for it. And also, I want to remind all of you that this event is meant to be very interactive. So please make sure to send your questions as we progress with our conversation. So, hello again, Christoph, and can you please introduce yourself to our viewers today? Thank you.
Thank you, Milena. So my name is Christoph Kapeller. I'm here located in Austria, working with g.tec Medical Engineering. So I studied biomedical engineering at the Technical University in Graz for my master's, and then did my PhD in Linz at the Johannes Kepler University in computer science. And I did many research projects together with g.tec throughout the progress of the thesis. And now here I'm responsible for the invasive device portfolio that we have, and that includes recording from the brain and stimulating into the brain with different neuromodulation protocols, including functional imaging and also brain-computer interfaces. So let's have a look how it looks like.
Yes, let's do it. I'm very curious to see this new edition of the device.
Okay, so here, this is now our new CortiQ 2 system. So it actually consists of a biosignal amplifier. This is the GI, then a switching unit to facilitate the routing between recording and the stimulation. So that's our brain stimulator, the eStim Pro. And here, that's our brain for today. It's the platinum silicon pad, an eco-grid that is in saline, salty water. And then we have here the cable connection via the head box to the recording input of the switching unit. And then we actually have here the interface, so a control computer and a screen to interact with a subject or patient. And then when we actually conduct the mapping, we have here our interactive view to the brain. And here you can already see that we localize the electrodes in a virtual brain. So what we need is the pre-surgical MRI and the post-surgical CT, and then we can localize the electrodes, for example, here for a patient that undergoes the epilepsy monitoring. So what we can do now is we can now measure if the electrodes are in good contact to the brain by means of the impedance. And then for different scenarios, for example, to prepare for an epilepsy resective surgery, to remove the seizure onset zone, we can now subvert this surgical planning with functional mapping. So here we know now which electrodes are in good contact and which electrodes are in bad contact. And then based on these locations that we now can record from, we can now here look at the brain activation that happens at the time of the recording. We have here the input. Of course, this is now from cell line. We don't really have brain waves. And then we can see here the high gamma activity. So the high gamma activity is a broadband change in the brain that happens beyond means frequency, usually beyond 50 or 60 hertz, depending on the country that we're located. And then we can associate that with different behavioral tasks. For example, you can do motor tasks and then understand where is a motor region in the brain on the cortex. We can do language tasks like the picture naming or word generation task, and by that we can ask the patient here on the patient screen to follow the instructions. So here this is the baseline condition, similar to fMRI, and then we create the difference in a block design manner between the resting and an active condition. And now the patient, for example, says this is a guitar or a horse, and through this mental process of the expressive language, we will see the brain activation on the map. And then finally, what we can also do is to go back to our electrodes on the brain, understand now which are in good contact, which are related to active brain regions, for example, the motor task. And then we can here now on the brain select the electrodes that we want to connect to the stimulator, and then stimulate electrical current into the brain and observe, for example, a movement response. And then this is associated with hand motor. And so now you can stimulate different areas on the brain that are maybe related to the epilepsy seizure onset, and by that understand if these areas that have to be resected maybe are also part of the allophane cortex, and that can include the motor area, the language area, but also the visual system. And all these areas can be stimulated, and we can observe the related symptoms.
Christoph, there is an echo that is happening, and it's very difficult to hear. Can you see maybe another microphone is still on?
So how is it now?
Yes, perfect. Perfect.
Okay.
Yes, thank you so much.
So I hope that you could hear the previous part properly. What is this?
So let me briefly check for headset. Can you hear me?
Yes, yes, Christoph, I can hear you. And can you please tell us who are the users of this system? Who are doing this type of research? Who can use the system for research or clinical purposes?
Yeah, so mainly for the clinical aspect. we want to address neurosurgeons and neurologists. But also, for example, if you have neuroscience research working with intracranial signals, or if you want to conduct neuromodulation experiments, many PhD students, postdocs, neuroscientists, neuropsychologists are interested in using this as a clinical research tool or a platform for their own recording and stimulation closed loop protocols.
Thank you. Would you be able to show us some of the examples of the research that is being done in this area?
Yeah, that would be great. So we can have a look into the studies.
Okay.
So one of the studies was, for example, that we have stimulated parts of the brain in the visual system, and we were mainly interested to understand if, when we, for example, have different visual categorization areas in the brain, and some are related to the recognition of faces. Sometimes, if resected parts in the brain cause symptoms like prosopagnosia, people are not able to recognize faces anymore. And that was the trigger for our study, where we studied the visual system more in detail. And what we can see here now is the brain response on the bottom left for different visual percepts. So the patient was actually exposed to presented faces, body parts, digits, hiragana, kanji, objects like line drawing objects and photos. And then we can see here the broadband changes for the high gamma activation here in Z-scores for different percepts. And we can see that approximately 200 milliseconds after a visual percept, that in the top left location, only the blue traces are like enhanced, and the remaining parts are flat. That means that this location only shows brain activation with respect to faces. Whereas if we go more posterior to the lower level visual categories, we can see that the responses are more similar between the categories. That means from posterior to anterior region, we go more to specialized regions. And this is the fusiform gyrus, which also includes the famous fusiform face area. But until this study, it was not 100% clear if this selectivity of the brain activation and also the symptoms that we can see when we stimulate that area, if that explains the responsibility of that particular cortex. For example, if only this tiny part of the cortex is responsible for the face recognition and processing. So now, with the explanation of the subject, what is the visual illusion during the stimulation, we can understand if, for example, different shapes exist for different objects, or only this visual processing of the face takes place. So here you can see in the top right the red bubbles. Those are the ones that are significantly different for face percepts compared to object percepts. And the purple bubbles, they are actually color preferred sites, so only for a colored image versus a grayscaled image differently on the cortex. So now when the subject is actually looking while electrical stimulation, for example, here to a box, then we can see that the patient explains that he sees some eyes and a nose and a mouth. And by that, we understand that there is a kind of a face fin, an illusory face that appears in front of the box. And of course, this can be caused by any visual property of the box. So we have to repeat that with, for example, other object like a round shape, different color, like a ball, which is more similar to a face. And then the symptom is exactly the same. So there is an overlay of a face on the ball. And the doctor now explains what the patient sees. And even when the doctor is stimulated, then the doctor is changing into a different person, and an anime face appears in front of the doctor's face. So with that, we now can explain what is the exact symptom and for which particular function this region is responsible. And that was not possible in previous studies because, for example, when monkeys are stimulated, they cannot respond what they actually see. They can only participate in the test. And the monkeys also joined the discrimination test between objects and sometimes failed when when the fusiform phase area is stimulated. But now with this explanation of the stimulation symptom, we can understand that there is a overlay of the phase in front of the object, so that might distract also the perception of the object, but doesn't change the object itself. And that's a very important finding in this study. So, so what we also learn, of course, is that the stimulation itself is a very difficult method to investigate. So it's very powerful because during surgeries, we can mimic lesions. We can understand what happens when we will resect that particular area in the near future, for example, interoperatively. But here we can also see that to understand what a particular brain region does is very difficult and subjective because it relies on the ability of the patient to explain what happens. So when we now look at, for example, these high gamma traces, we can already from the contrast that we have defined from visual percepts, we already can infer what is the special functionality of this particular cortex.
Yes, thank you so much, Christoph. So, what are the main challenges in this type of study, and how can they be addressed by using maybe a different setup or adding some other tools or
I think it's very important that we
Mhm,
combine different imaging techniques to get a clear picture of what's going on. So, for example, there are different ways to obtain functional imaging. For example, pre-surgical fMRI, you can conduct TMS, you can do the WADA test to sedate parts of the brain, you can electrically stimulate the brain, and you can record from the brain. And with all these methods, you get, of course, different insights, but also different complexity levels that you have to account for and risks, of course. So now the question is, when we overlay this, we can also go to another study that we have conducted with the Asakawa Medical University to better understand and fine-tune the different protocols that we can implement for actually the visual categorization on the ventral temporal cortex, for example, for face recognition. So here on the lower left part, we can already see the dynamics in the brain when we get a face presented and observe the face, so that here we can see after about 200 milliseconds after the stimulus onset, we get this burst of high gamma activation in the brain on different areas. So here you can see like slightly green or beige, the fusiform gyrus, and mainly on this fusiform gyrus, we get this response with respect to the faces. And we can perform the same experiment also in the MRI scanner with an fMRI protocol, and we can measure the blood oxygen level dependency for different face percepts and object percepts, and then get the t-value of the bold difference between the object perception and the face perception in the brain. And here in green color, the balls show us the significant t-values for face percepts compared to object percepts. And again, they are mainly located here on the fusiform gyrus.
yeah.
The problem with the fMRI is that in like reddish color, you can already see some bubbles that are actually on the anterior part of the temporal lobe, on the ventral temporal lobe, and those are artifacts that are invisible because of the ear canal. And this is a very weak aspect, for example, in fMRI, although it's very helpful for the pre-surgical evaluation. And then on the right side, we can see the superimposed image between the electrical stimulation that we have seen in the study before and the fMRI and the high gamma mapping with electrocorticography. And what is very interesting is that only here in 2 out of 5 subjects, we got this good explanation of the visual illusion that is related to this face overlay, where 3 subjects couldn't report that. On the other hand, even in subjects that couldn't report that, we found significant changes in electrophysiological high gamma or in the hemodynamic bold response on similar locations. And interesting is that the electrocorticography, the high gamma biomarker, just co-localized either with cortical stimulation or with the fMRI bold most, whereas the fMRI turned out to be the most sensitive one, also with most false positive regions, and the cortical stimulation was the least sensitive one. So that is also an implication that tells us that it's very difficult to conduct precise cortical stimulation mapping.
Very interesting. So we can use stimulation alone. We can combine it with the gamma mapping and with other functional imaging modalities for precise localization and to really get in depth of the processing. And the next, what would be the next step? Because of course we're all right now interested in certain BCI application. So what can we do as an output of the system?
So now that we can measure brain activation, we are also interested in observing what's going on in the brain and conduct this kind of a feedback loop or a control signal, so to say, for brain-computer interfaces. So the first step was to translate the functional related areas into kind of a monitoring output to, in real time, decode what's happening in the visual system in the brain. And in this study here, together with the University of Tokyo Hospital and also the Asakawa Medical University in Japan, we actually tested the decoding of visual perception and the discrimination of different visual categories, including kanjis, faces, and no related visual perception. And for this, we now switch from our closed clinical software, the CortiQ, into a Matlab environment that is actually utilizing a toolbox that is called Simulink. And this toolbox is able to perform online calculations. And with each time slot that the amplifier delivers data, gives us an output value of processed data. And we can, of course, define how we process the data. So here we filtered the data in the high gamma band and then also combined the channels with a common special pattern analysis and then sent these feature channels into a linear discriminant analysis to distinguish between phase percepts, kanji percepts, and no or different percepts. And on the video, you can also see the different like monitoring feedback that we get when the patient is actually looking at different percepts. So you can activate the video in the lower right bottom, right? And now we can see whenever the patient sees a face or a kanji immediately, that means approximately 300 milliseconds later, we get a feedback what the patient has seen at that time. And on the right side, you can see also in red when the features are exceeding, based on the brain activation, a threshold, and then they're categorized as face or as kanji. So now that we can extract that information in real time and also make a decision what happens in the brain, we can also, of course, do that for other areas.
Yes, definitely we can do that. And many people who are working in the field, they're interested in application for avatar control, for robotics. Yes, so what studies would you recommend for that purpose to look into? Mhm.
So the question is how we can actually translate high-level commands from the from the patient or from the subject into control signals. And of course, we can, for example, work on individual finger movement decoding. Or here, this is an experiment where we actually classified between different gestures. And in another experiment that is also similar, we actually calibrated a humanoid robot to perform a grasping task by itself. So with different levels of like context awareness in the system. And here in this particular study that we have, we can actually see how to discriminate between like rock, paper, scissors gestures, and then immediately send the output from the brain activation, again, the high gamma band, and then spatially filtered for different common spatial patterns. And those feature channels are then generating again a very easily distinguishable output signal that can be translated in an open or relaxed hand, in a peace sign, or in a rock.
Yes, that's absolutely amazing. And let's let our viewers to see this demonstration on the lower right side. How how
So here
it
we can now see in the screen the open hand, and the patient is looking at the screen as a cue. And now we have the peace sign, and then the robotic hand actually performs the peace sign as an received control input from the brain signals. So at each time the amplifiers acquires data, we will actually update the, the features and then make a new decision and send this decision to the hand.
yeah, that is very impressive. Thank you so much, Christoph. And I'm also very curious about more clinically oriented studies or clinical application of the system. How can we use this knowledge about the gamma activity, increase in gamma activity, and maybe certain behavioral measures?
So the good thing on the high gamma activation is that it can be very generalized. So we have seen that in the visual system, we get a very strong high gamma response in the motor system, but also, for example, in the language area. So there's the expressive and the receptive language area and all these parts that are connected when we perform, for example, um, yeah, a picture naming task or verb generation task. And what is very interesting is also to understand when we electrically stimulate the brain behaves differently depending on the region. So for example, when we stimulate the language network, then it's very likely to occur a speech arrest called aphasia. So when we stimulate in particular regions of the brain, then the patient loses the ability to talk. And we wanted to understand how the brain activity actually tells us about the symptom that will be elicited by the electrical stimulation. So this study we actually conducted with Dr. Kamada, who is now at the Chitose City Hospital in Japan. And here you can see in the yellow traces the time of the stimulation after a person is actually asked to say what they see in a presented picture. And then we can actually, we can now see the person is presented with an egg called tamago in Japanese, and then she has to explain what she see. And during the stimulation, she cannot do that. That's called aphasia. And now we're interested when in the time of the brain processing this symptom will actually triggered. And what's very interesting is when we only look at the sham stimulation, we can see here on the top, on the bottom left, the time frequency map, where we see the low frequency and suppression in blue, and as a red blob, the high gamma or broadband activation in the brain. So on the bottom left, you can see the frequencies from 0 to 150, right? And then in gray, this is the time when the stimulus is presented, and then we can see in the sonogram just above when the patient is actually saying tamago. And the high gamma activation is just shortly before the expression. So now when we stimulate into different times of this high gamma activation, we can actually learn that the high gamma peak will define the transition from a very effective and symptomatic stimulation to actually no or less symptoms during the stimulation. And the interesting thing is that this can also be changed for different subjects. So for example, if the subject is faster, the high gamma peak will also be earlier, and our stimulation time has to be adjusted caused by that. So this is very interesting because the brain activation tells us what symptom will happen depending on the stimulation protocol.
Yes, yes. So it's important to have this individualized stimulation based on actual brain activity measures that we can do in real time. Yes. Okay. Thank you. Thank you so much, Christoph. I also know that there is opportunity to look at the language network even during the um, awake craniotomy. So can you tell please about this type of studies? Because I think that is so much important as some people need to go through language mapping during awake craniotomies. Can you tell a little bit more about this type of studies and why they're important, and just provide some example of those?
Sure. So basically, what is also interesting is to, of course, in the epilepsy monitoring unit to perform all these tests, but during the progress of a surgery, it's also necessary, for example, when the speech network is affected or in close proximity, for example, to a brain tumor, that you can accurately remove the brain tumor, but also preserve the ability to speak. So one way is to do an awake surgery where the patient is actually talking during the progress of the surgery, and you can mimic the resection with a handheld probe where you stimulate and touch parts of the cortex. What you also can do is that you, for example, like in this picture, place grids and record the brain activity when the person here is now presented with linguistic sound. So the person hears a story, and then we can measure the brain activation while this story is perceived. And what is very interesting is that this can also be done at BIS levels below 90. So for example, at 80 to 85, this is the transition where we can actually measure nicely the high gamma activation already for story listening, but the patient is still sedated. And also what is interesting is when we now stimulate into these areas, here we get, of course, illusory effects, but this is the temporal lobe. And now when we look at the frontal lobe, when we stimulate into the areas with a single pulse, we can elicit evoked responses as a measure of connectivity. And these are called cortical evoked potentials. And these CCEPs on the frontal lobe now tell us which areas are interconnected with our network that we have revealed during the passive listening task. So now when we stimulate, for example, in the complete awake period into these evoked potentials, we can observe similar effects like the aphasia that we had in the case before. And with this, we get a more detailed understanding how different like areas in the brain are interconnected and working together. And that is, of course, important for the speech network. And with, for example, additional fiber tracking techniques, we can now reveal between the stimulation entry point and the evoked responses, the fiber tracks that are connecting these networks.
Yeah, that is absolutely, absolutely amazing. So you can integrate fiber tracking into the system as well. Do I understand correctly?
Yes, so any
Mhm.
nifty or segmented patch file like a VTK or
Mhm.
STL or object file that also represents, for example, fiber track from any DTI processing software can be added as a layer and visualized on top of the brain mapping results together.
Thank you so much, Christoph. And maybe we can switch to the demo and we will see if we have also questions from our audience that we can answer. But that's
Sure.
very, very impressive. Thank you so much. So
You're
I'm
welcome. So I've prepared also an Matlab example, so give you a bit of an understanding how to actually work with this like decoding or brain-computer interface online processing platform that we call g.tec, the high-speed online processing in Simulink. So what we need to establish is a Simulink model that actually has data sources. So this can be our amplifier, or in that case, to prepare for an upcoming experiment, a file that we have previously recorded. And here you can see this is a MAT file with a sampling rate of 1200 Hertz. And then the data is actually processed, for example, through visualization filters to show it in the scope, to see the raw data. Then there is a feature extraction, so we can see the high gamma between 110 to 140 Hertz. So 50 and 100 Hertz are the main frequency and harmonics. And then we calculate the C-squared logarithmic band power, so the normalized power in the brain that reflects the brain activity. And also we have the common special patterns and variance and normalization steps, and then a linear discriminant analysis, and then the classifier output. So when all of this is defined, then we can actually start here the Simulink model. And then here we actually have the feedback block, and that is in this case now a Unity program. So here we can actually see a virtual avatar that is from our hand pose experiment that we have seen in the previous study. And here you can see the queue, and that is actually the feedback. So now let's have a look at the different endpoints. So this is a visualization endpoint. This is the feature scope endpoint, and this is the classifier output. And this is, of course, the feedback now. So when we now arrange that a bit, we can make a test run to see if our processing pipeline is good. So here you can now see the raw data coming in, usually with a visualization filter here from 2 to 90 Hertz. Then this is our high gamma activity at the time of each processing step. And this is our classifier output. So now on the queue, you see that there's a peace sign. And then we have here on the brain the pattern for peace. And in the feature scope, we can see how the features are lifted based on the movement. Like again here, for example, this augmentation here in the scope, this is related to the peace, and that's a linear combination of all the channels of high gamma. So here we can see actually the features in real time, and then these are the linear combination of the features into combined channels that are then used for classification.
Thank you. Thank you so much, Christoph. My next question is about the neuromodulation, which becomes more and more popular as the time goes on. In what areas can this system be used for neuromodulation, and of course simultaneous recording of the data? What are the latest trends?
So, of course, many of the neuromodulation applications are in clinical research. So there's a responsive neurostimulation, for example, for epilepsy to terminate seizures or to treat seizures by recording and stimulating. Then, of course, there's the possibility if you have stimulation induced after discharges, you could also terminate the after discharges with a stimulation. There are use cases, for example, for deep brain stimulation or adaptive deep brain stimulation based on beta band power, where you can then, for example, treat tremor, Parkinson, or also psychiatric disorders. And just in any case, for example, here we now classify based on thresholds of high gamma activation. We could simply change this, for example, into whatever, like 12 to 30 hertz, and then have a low frequency band, including beta band power, that could be interesting, for example, as a trigger for DBS. So what we now can do is here simply add a stimulator block and then trigger the stimulation here, and then have a threshold and combine the threshold with the feature. And then, for example, if the filter data for any band power or oscillation exceeds a threshold, we could then start the stimulation. So it's very easy with this prototyping platform to combine decoding and stimulation protocols for open closed loop feedback and stimulation experiments.
Thank you so much. One of the questions we were sent beforehand was about stereo EEG. So you mentioned several studies, and in those studies, mostly people used grids. However, there is now a preponderance for using stereo EEG and for surgical purposes. And of course, this is also used as a research tool when used in the same patient. So, what are the opportunities of using stereo EEG with this system?
So first of all, of course, the system can handle both the grid and the stereo EEG. And the input is always a montage. So when we go here into the montage part, then we first have to define our sensor location. And I think there are like two major fields. So one is the interoperative treatment, where the majority of the cases has to use grids because you can flexibly place them on the exposed area on the cortex that is open in a craniotomy. But the other aspect is, of course, when we go to epilepsy monitoring and also to the treatment of psychotic disorders or DBS, for example, to test different stimulation protocols, then in those cases, the majority are with stereo EEG or depth electrodes. And at the beginning of each treatment, intervention, or like monitoring, there is the placement of the electrodes. And here we can start, for example, with ECOG and stereo EEG. And with each modality, you can have different localization techniques. So here you can see those are the blobs of the post-surgical CT, and these are our sensor locations. And now we can here from a database select the shaft that we want to implant or that we have already implanted, and then snap it to the CT artifact. And then we have a very good co-registration of the electrodes and the location in the brain. So we know where in the brain are our electrodes located. And from here, we don't care anymore whether or not this is a white matter, gray matter electrode, because we can simply obtain the biomarker, for example, high gamma activation, that also works with stereo EEG. Of course, if we have, for example, here gray matter excess in the motor cortex, then we will also see the task-related changes. We can also stimulate in a bipolar manner, and of course, trigger, for example, for responsive neurostimulation or any other stimulation protocol, open and closed loop.
Thank you so much. I think there is a great potential in using this tool in both clinical and research aspects. Um, is there anything that maybe we haven't covered today yet, but you think it would be important to mention to our viewers?
Well, in principle, we are always trying to be on the latest trend. So if you're interested also in working together with us for studies, then we are usually very cooperative with our customers. So if they have any customization that is beyond our product standard, then usually we support everybody to get like the latest requirements for their studies. So this is usually how we work with the customers to really optimize protocols for their needs. So I think that gives a very good perspective.
Thank you. Thank you very much. Can you see my screen, Christoph?
Yes, it looks good. So if you have follow-up questions, please contact us. You can directly write me an email at kapeller@g.tec.at. You can also visit our website to learn more about our system and how all these parts can be connected and assembled and different variants. And again, please let us know if we can help, and we are happy to support.
Thank you. Thank you so much, Christoph. I think that was a very, very insightful conversation. And of course, I wish you a great progress further and keeping up with innovations and supporting people in their amazing research. So thank you so much. Thank you for everyone who listened to us today, and looking forward to seeing you in our future LinkedIn Live events. Thank you.
Thank you very
Bye.
much, Milena.